All right, hello everyone. So today we're going to talk about hypothesis testing. So the book just has a lot of examples in it, and so I'm going to do those myself because there's a 8-step process that the book does not teach that I want you guys to learn. So I'm going to demonstrate that on 5 examples today. Here are the objectives. So we want to conduct a complete hypothesis test for, and then there's 3 different scenarios. There's the mean, where the sigma is known, mean where sigma is unknown, and remember sigma here is the population standard deviation. And then there's the scenario of looking for a proportion. Okay, and notice that some of these are z-tests and some of these are t-tests. And so we'll discuss that. And then identify all steps to the formal hypothesis testing procedure and apply them consistently. Right, yes, of course. Okay, very good. Now, this right here, this lesson guide is designed to go with a video, and I'm going to put in the link after I'm done with the video. Now, do read the book and fill these in. The instruction in the book there's not very much there. It's just a lot of examples as well, but do read what little instruction there is in the book here and fill in these 4 vocabulary words. Now I've summarized the key facts of section 5.9 here. I've included this summary here. You'll see that the significance level is what we compare the p-value to. If the p-value is less than the significance level, then our data is significant. It's sufficiently rare. On the other hand, if the p-value is greater than the significance level, then the data is not significant, not rare, does not stand as evidence against the null hypothesis. Okay, now there's no table like this one here in the book, which is unfortunate because it's a very handy table. All right, so in order to determine the tailedness of your test, all you need to look at is the alternative hypothesis, okay? H1 or HA. Now, if the alternative hypothesis has a less than in it, then it's going to be a left-tailed test. Now, why is that? Well, if the alternative hypothesis has a less than in it, then the null hypothesis could be written like this. Well, let's say that this was with mu less than mu naught. That's our alternative hypothesis. Well, then our null hypothesis was something like mu greater than or equal to mu naught. Of course, I like to just always consider the null hypothesis as having equality. But the opposite of this alternative, of this hypothesis, would be with greater than or equal to. Now, if we are trying to disprove that something is greater than or equal to this mu naught, then it's not going to disprove it if we find data in this region here, right? That's going to be in support of this null hypothesis. So we don't look at that. We look at just what's over here in contravention to the null hypothesis. Okay, it's the same thing here. If your alternative has greater than, then your null hypothesis, the opposite of this, is less than. Any data that we find that's over here, less than the mean, is not going to stand in opposition to the null hypothesis. It will not support the alternative. And so we are looking for a right-tailed test. The p-value is the area on the right, which represents the likelihood of getting data as extreme or more extreme in opposition to the null hypothesis. All right, and then if it's not equal to, then the null hypothesis was equal to, and notice that either one of these violates the null hypothesis. And so we include both of those areas as our p-value. All right, but now it would be great if you understood why it is that way, but if you don't, this right here is just what you can memorize, and that'll certainly get you by. Okay, let's go ahead and take an example. Now, I want you to do the two next examples. I'm just going to do this first one here. So the area of the shaded region is the p-value, exclamation point. That's very important. The shaded region itself is determined by the test and your data value. Okay, so example 9.11, you've got the null hypothesis is mu equals 5. Well, mu is right there, right? That's the mean of this normal distribution. And that's our data, follows this normal distribution. Now, our alternative hypothesis is that mu is less than 5. And our data here is 3.2. So the p-value then, because it's less than, this is going to be a left-tailed test, which is what I want to put right here. The p-value is going to be this area here. The area is the probability. The probability is the p-value. So the area is the p-value. And it's only on the left. It's these values here of my data that is going to be as extreme or more extreme in opposition to my null hypothesis. See, again, if there was data over here, that would not oppose my null hypothesis, which can be regarded as the opposite of my alternative hypothesis, which can be written like that. Data over here would not disprove this, and so I'm not going to consider that. I'm looking to see if my data disproves the null hypothesis in favor of the alternative. Okay, so go ahead and fill out the rest of these in a like fashion. And now let's talk about the 8 steps. Okay, so the first step, now the first 3 steps we have seen before. First is to identify the original claim. Next thing, and write it in math. So I'll just say that, put in math notation. Next thing to do would be to take the opposite of the original claim. So this is negate original claim. Also put in math notation. Once you have those, it's easy to see which one is going to be null hypothesis and which one is going to be the alternative. The null hypothesis is the one, either the OC or OOC with equality. And then we make it strict equality. Okay, so that means no greater than or equal to, just equal to. No less than or equal to, just equal to. And then this thing right here is the leftovers. All right, so whichever one did not get used for the null hypothesis, either the OC or the OOC. That becomes the alternative hypothesis. Okay, then you need to state the preconceived significance level, and the default value there is 0.05. So we default, that means we default to 95% confidence. Okay, identify test and compute test statistic. So you'll remember from before, I think it was day 7, no, it was day 8, where we talked about the different tests. Okay, you need to identify the test and find that test statistic. And remember from last time on day 19, we said the test statistic is the z-score of the data, right? We get this data value, we get this sample mean. We take the z-score of that sample mean. That is our test statistic. Identify tailedness and compute p-value. So to identify tailedness amounts to nothing more than analyzing the alternative hypothesis. Once you know what tail you need, and you have the distribution of the test statistic, you can then compute the probability. And that's what we're looking for, that probability. Okay, then what you do is you make your decision. We have this decision rule. If the p-value is less than alpha, then we reject the null, because the probability of me getting data as extreme or more extreme is very, very small. It's just like when Allie reached into that basket. No, who was it? It was the other girl who reached into the basket. I don't remember what her name was. She reached into that basket and she pulled out a plastic ball with a $100 bill. It was she was the very first one to do that. Strongly suggests to me that the assumption that there is only one $100 bill in all 200 of those bubbles is false. It suggests that it's false. We are using the same sort of thinking here. If the p-value is less than my alpha, then to get data like mine on a first go is too unlikely. Too unlikely. And so something's wrong. Now, a bunch of things could be wrong, but really we're going to isolate it. The weakest link is this population parameter assumption. So we reject the null, which is a population parameter assumption. That is the thinnest ice, and that's what's going to get the blame for when my p-value is way too low. Now, on the other hand, if the p-value is not smaller than alpha, then the data is normal, and so we do not reject. It's not calling my data unusual. It's like if that girl reached up and did not get a $100 bill. It's not unusual. Or if somebody said, yeah, half of those plastic bubbles are $100 bills, and she grabbed one, that's not unusual, right? I've got no grounds on which to reject the null hypothesis. Okay, now we're going to state the conclusion. And the conclusion has a number of important guidelines that I would like to impose. One, first thing you do is you state whether there is evidence or not. And what is the evidence? That's the data. The data is the evidence. When that girl reached up and grabbed that plastic bubble with a $100 bill in it, that was her experience. That's her evidence. And that's Allie's evidence to say, there's probably not just one in all of those 200. So you need to state whether there's evidence or not. And then what you need to do is you need to report p-value. Then you need to make sure that the conclusion is in terms of original claim. And it's free of jargon. Okay, we want it to be as accessible and understandable as possible. So you're not going to say null hypothesis. You're not going to say alternative hypothesis. You're not going to use any sort of jargon like that. You're just going to say in terms of the original claim. Can we support or can we reject the original claim? Okay, and then the last thing that you need is the confidence level. You got to report the confidence level. Okay, now let's focus in for just a moment on step 5. Okay, you got to identify the test and compute the test statistics. So you've got these. So we're going to see a lot of tests. Okay, we're going to see 14 tests by the time we're done. Today we're just learning 3 of them, and these are the 3 tests. You've got a single population. Where is it? Population 1. A single population, and there's a proportion. All right, it's not talking about a mean, it's talking about a proportion. Well, if that's the case, then that's test 1. Now, what's the test statistic for test 1? It's this right here. Where did it come from? You take your data and you put it on the distribution that we get from the CLT, from the central limit theorem, and you find the probability of getting data as extreme or more extreme. What we do here, this test statistic, is this is just a z-score. Notice that p hat, or rather p prime is how they like to put it in the book, p prime, by the central limit theorem, is normally distributed with the mean being the population assumption, okay? This right here. See, p equals p naught. That p is the true mean of the population, and by central limit theorem, that's the true mean of the sample statistic. And then what's the standard deviation? Well, remember what we did on day 18, I think it was? We found the standard error of a population of a sample proportion. And that was it right there, right? That was our distribution. Notice that this test statistic is nothing other than the z-score. You subtract the mean, you divide by the standard deviation. So it's a z-score. Well, z-scores are always normally distributed. Okay, so in order to find the p-value, what are we going to do? We're going to find the probability using norm.dist, and we're going to put in that z-score. That's my cursive z. And then we're going to do 0 for the mean, 1 for the standard deviation, and 1 for the cumulative parameter, as always. And so this is going to be that probability. Now notice that this is only the equation if it's a left-tailed test. If it's a right-tailed test, you do 1 minus norm.dist. Because that'll give you the amount that's to the right of my z-score. And if it's a two-tailed test, you can go, 2 times norm.dist of z. Now, if you've got to make sure that this thing here is negative. If my z-score is positive, I give it a negative. If it's already negative, I keep it as a negative. 2 times that tail. 0, 1, 1. 2 times the tail. Okay, that was test 1 if it's a sample proportion. The next two tests are both sample means. Now, there's a difference between them. One is whether you know sigma, and the other is whether you don't know sigma. But again, we still have one quantitative variable. Now, that's in opposition to this one here. Remember, this one we had one categorical variable. And it was either yes or no, and it was a proportion of yeses. This one here is a quantitative variable, and we're taking a mean. Again, there's just a single population, just one group of people. All right. Okay, we'll talk about the assumptions in class, but notice again that this is a z-score and that the z is a standard normal distribution. Okay, now, if sigma is unknown, right, if we don't know the standard deviation, if we don't know the standard deviation of test scores or something like that, which is very common, then this z-score here that we would get, see, we have to use S to approximate our sigma because we don't know sigma, but we use S. As it turns out, if you use S, this is not normally distributed. This test statistic is not standard normal distributed. It's actually student T distributed, right, which is close, but not exactly. So just remember a few facts of the T distribution is it's bell-shaped, but it's a little wider, right? It's a tiny bit wider than the normal distribution, depending on the degrees of freedom. The higher the degrees of freedom, the closer T is to the normal distribution. Okay, so those are the three tests we're looking at. Let's go into an example. Jeffrey, as an 8-year-old boy, established a mean time of 16.43 seconds for swimming the 25-yard freestyle. So that's his average, with a standard deviation of 0.8. Now, he established that, right? So this right here is going to be my population mean. This thing here is going to be my population standard deviation. Notice that it does not say that that's the standard deviation of a single sample of times. It's the established standard deviation. So that's sigma. These are population parameters. Okay, his dad, Frank, thought that Jeffrey could swim the 25-yard freestyle faster using goggles. Frank bought Jeff a new pair of expensive goggles and timed him for 15 25-yard freestyle swims. For the 15 swim, Jeffrey's mean time was 16 seconds. Frank thought that the goggles helped Jeffrey to swim faster than the 16.43 that he previously established. Conduct a hypothesis test using a preset alpha of 0.05. Okay, so we're going to start with a 95% confidence on this test. Assume that the swim times for the 25-yard freestyle are normal. Right. Will do. Okay, so step 1. Well, you know what? Let's go to Excel. All right. Let's go let's find Excel. Here it is. Go to create. Let's get a new one going here. All right, so this right here is, we'll call it swim times. Step 1. What is step 1? Original claim. What's the original claim? What are we trying to test here? Conduct a hypothesis test using a preset value there. Okay, what does it say? Assume that the swim times are normal. Frank thought that the goggles helped. Okay, that's the thing that we're trying to test, okay? Frank thought that the goggles helped. That's the thing that's in question. But did it really? Right? That's sort of the implication here. Did it really? Was that statistically significant? Let's find out. All right, so I'm going to say mu, option M gives you mu. If you have auto cap on, it'll just look like a M, which happens to be a capital mu. But if you don't have auto cap and you put option N, then you'll get a mu. So Frank is saying that mu is less than, no, let's see now. Mu equals, no, mu is less than 16.43. All right, let me just go back. Now, how did I get that? Swims faster than, see, Frank thought that with the goggles, Jeffrey swims faster than the 16.43, meaning his time is a bit less. So this would be less than or equal to, faster than is just strictly less than, isn't it? Faster does not include equality. Step 2, the opposite of the original claim. Let's go ahead and negate this. Mu, whoops, if you do control M, it minimizes it. Mu is less than, greater than or equal to 16.43, right? That would be the alternative of it being less than that. Okay, step 3. Well, which one has equality? Well, that would be the second one, the opposite of the original claim. So that's going to go to my null hypothesis. So this is mu equals, oh, it's always equals. The null hypothesis is always equals. The alternative is the leftovers, which in this case is this one, Command C, Command V, boom. Step 4, they gave me alpha. Alpha equals 0. Oh, I quite forgot what it was, 0.5. Yep, there it is at the very bottom. It started the bottom line. 0.5. That's my alpha. Step 5. I've got to identify the test. Okay, well, what am I dealing with here? So it's definitely a mean. I mean, do you agree? It's a mean. And we do know the actual standard deviation, the population standard deviation that was established is 0.8. So let's go ahead and go with that. Let's go with that. So because I know the population standard deviation, I am looking at test number 2. I've got a known sigma. All right, so I'm going to take a look at this test statistic here. That's the one I'm going to use. Okay, now, looking at the assumptions is also very important. Do I have a simple random sample? Near enough. Is the population is normally distributed or sample size is large. Notice, is that familiar? That's the central limit theorem requirement. So, of course, the central limit theorem has to be met because the central limit theorem is the foundation of the theory behind these hypothesis tests. All right, so here I go. I am going to do test. This is test 2. So it's going to be z equals in the end. Okay, now what do I need in order to get that? Well, I need my x bar, right? I need my mu. Whoops, minimize it again. I need my mu. I need my n. And then I think that's everything. So what is x bar? Well, it's 16. You'll recall that when Frank timed him for 25, scroll down here again. Yeah, no, 15. 15 freestyle runs. The mean was 16. But what about mu? I need mu. Well, mu is going to be 16.43. Why is that? That's the null hypothesis told me so. Okay, so the z-score is going to be equals, parenthesis, x bar minus mu divided by, parenthesis, sigma. Oh, I forgot to put in sigma. Sigma will go right there in that cell. Divided by square root of n. Close parenthesis for the denominator. Enter. Yeah, divided by 0, because I haven't put in my sigma yet. Okay, sigma is going to equal 0.8. Enter. Okay, there's my z-score, -2. -2.08. So notice, let me just take a look at that again. That right there, that is exactly the formula that we had as our z-score, right there. Okay, we are done with step 5. We identified the test and we got the test statistic. Time for step 6 now. P-value. Well, the p-val is going to equal, okay, is this a right-tailed test, a left-tailed test, or a two-tailed test? Well, all I need to do is look at the alternative hypothesis. I see less than, less than, that's a left-tailed test, left-tailed. Okay, and so if it's a left-tailed test, I'm looking for the area to the left, which is exactly what Excel naturally gives me. So I'm going to do norm.dis, norm because this is normally distributed. That's what test 2 is. I'm going to put in my test statistic right there. Mean is 0, standard deviation is 1, and cumulative is 1. I'm going to push this. I'm going to get the probability, right? This is the area to the left. I'm going to get the probability of getting data as extreme or more extreme than that sample that Frank got from those 15 25-yard swims. 0.018. Okay, step 7, the decision step. Is p-val less than alpha? Answer: yes. Okay, so what does that tell me? It tells me that my p-value is sufficiently rare. Like if it really was, if the true mean was 16.43, then the likelihood of me sampling out of 15 runs an average of 16, something as low as 16, that is just too unlikely to believe. So I'm going to reject the null. All right, step 8. Okay, so I'm rejecting the null. There is evidence. There is evidence. And what's the nature of my evidence? What's the strength of my evidence? P equals, I put in my p-value, 0.018. Yeah, let's leave it at that. In fact, let's go 19. Okay, so that's 3 decimal places. There is evidence. 2. Okay, now, it is in terms of my original claim. And the original claim is my alternative hypothesis. So, since I am rejecting the null, I am supporting the alternative hypothesis, which is my original claim. And since I want to talk in terms of my original claim, I am going to talk in terms of supporting my alternative. So that means that there is evidence to suggest that Jeffrey swims faster than with goggles. Right? Because that mean of 16 from 15 swims couldn't have been a fluke. All right? It was way unlikely, given the null hypothesis, for that to have been a fluke. Yeah. So there it is. But I almost forgot my confidence. I'm going to say with 95% confidence. Okay, and so there it is. I'm going to take a screenshot. I hope you will take a screenshot. There we go. And what am I going to do? I'm going to go copy and delete. I'm going to go back here. Okay, so please put in a screenshot. I want you guys to be doing these examples. Okay, and so this is a way to incentivize you to get into Excel and do this work, this example. It'll be very, very helpful to you, I believe. All right, there it is. There's our first example. There's my conclusion. Googles. I said Googles, though. Oh, well. Hopefully you put goggles. Okay, let's go on to the next one. A college football coach records the mean weight that the players can bench press as 275 pounds with a standard deviation of 55 pounds. Okay, right? So some can lift more, some can lift less. And the spread is about, there's a standard deviation of 55 pounds. 3 of the players thought that the mean weight was more than that amount, okay? They asked 30 of their teammates for their estimated maximum lift on the bench press exercise. The data ranged from 205 pounds to 385 pounds. The actual different weights were, and here's the frequencies. Okay, so there it all is. Conduct a hypothesis test using a 25% significance, 2.5% level of significance to determine if the bench press mean is in fact more than 275. Okay, great. Let's go ahead and do this. So what I'm going to need to do, I'm going to hop over to Excel, right? But what I need is my data. So I'm going to go ahead and get my data. Let's see. Whoops, let me see. I want to get all of it. There we go. Copy. Go to Excel. Let's see. Do I want a new sheet? I'll just go down a ways. Okay, so what do we have right here? This is, what was the context again? College football bench press. I'm just going to call this one football. All right, so let's do, let me just paste, go to draw. There's my paste. I pushed Control V. Okay, so there's my data. All right, so before we do anything else, let's go ahead and do step 1, the original claim. Whoops, original claim. All right, great. So the original claim was, let's take a look at this, that the data from 245, the actual weights were, 3 players thought that the mean weight was more than that amount. Okay, I think that's our original claim. The true mean bench press of all players on the team was more than 275. So at the so that translates to mu is greater than 275. Step 2, the opposite of the original claim is that the true mean bench press was not more than 275. How do I write that? I write mu was less than or equal to 275, because that's the opposite of the notation for the first claim. Step 3. The null hypothesis. I bet you guys already know what this is going to be. This is going to be mu equals 275, and the alternative is the leftovers, so that's going to be this one again. Copy, paste. There we go. Okay, now let me do some things that'll make this easier for me later on. So what kind of a tail is this, or what kind of a test is this? Well, it's a right tail test, right? Because the alternative hypothesis is greater than. Okay, and then also, which one was the original claim? Well, the original claim was the alternative hypothesis, right? So this one here is the original claim. So for step 8, I'm going to say suggest or support. Maybe support would be better. Let's say support. Oh gosh, support. Awesome. All right, very good. Now what? So I'm going to support. Let's go to, and that's even before I know what my conclusion is going to be. I know I'm either going to fail to support or support this claim. Okay, well, let's see what the data shows. So this is going to be alpha equals, my significance level is actually 0.025, if I'm not mistaken. Yeah, 0.025, because that's my significance level. All right, step 5. What kind of a test is this? Well, this has got to be test 3. Why? Because it's about a mean with no sigma, okay? No population standard deviation. I don't see one anywhere. Okay, so actually, we do have a standard deviation there. So this will be the same test as before, test 2. Because we do have a sigma, with sigma equals 55 pounds. All right, right on. So let's go ahead and do this then. So that's going to be z equals, now what do we need in order to get this? Well, we need x bar, we need mu, we need sigma, and we need n. Okay, now, for x bar, we are going to need to put in our data. So off to the side here, I'm just going to put in some data here. 205, and the frequency was 3. All right, and then there was 215, and the frequency for that was also 3. And so on. Okay, so now I have all the data from the coach. Okay, so look, so 3 people were able to bench a max of 215. 5 people were able to bench a max of 316. And if I sum all of those together, I get 30, which is how many I should have in that sample. Okay, well now what I need to do is get the mean. And so I'm going to do equals this times this, enter. Okay, so that's how many, so that's the total contribution from all the people who can bench a max of 205. Okay, I'm going to autofill that down, and then I'm going to take the sum here. And there's my sum. Now in order to get my mean, which is x bar, I need to divide this by this. There it is, 286. 286. So that's what I'm going to put in for my x bar. I found the mean from the sample. So 286 point, let's go 0.2. Okay, now mu is 275. It says it right there in the null hypothesis. All right, now sigma was 55. We established that, and n is 30. Okay, now what I want to do before I compute z is take this standard error. So I'm just going to find that standard error equals sigma divided by square root of 30. That's my standard error. And now I can do my z-score. My z-score is going to be x bar minus mu, close parenthesis, divided by standard error equals 1.11, 1 standard deviation above the mean. So that's where my data lies on this distribution, assuming that what coach said was true. Okay, so let's go with step 6. I need to find the p-value. So p-val is going to equal, okay, now is this a right-tailed test, a two-tailed test? It's a right-tailed test. We already saw that, right? So I need the right tail. So this is going to be 1 minus norm dot dis, with the x value being my z-score. The mean is 0, standard deviation is 1, because it's a z-score, right? And those are always standard, normal, distributed. All right, I'm going to press enter. There it is, 13%. Step 7. Let's see, what have we got here? Step 7. Is p-val less than alpha? The answer is no, it's not. It's not. See, so my data is not as rare. I mean, my data is pretty compatible. It's not rare compared to what coach said. Coach was, okay, kind of, maybe he's right. So I'm going to fail to reject. Step 8, I'm failing to reject. I don't have evidence to reject, so I'm going to say there is insufficient evidence Okay, what's the strength of my evidence? P equals 0.132. Not very strong evidence, right? Because that P is the probability of getting data like this is not all that small. There is insufficient evidence to support. Remember, I'm going to use support. That's step 3, way back in step 3. There's insufficient evidence to support the claim that the mean bench press is greater than 275 with 95% confidence. Okay, so what happened here, right? Because my mean bench press, the mean of all the of my sample was 286, right? Was 286. That's 10 pounds off or 11 pounds off, right? Isn't that different? Yeah, it's way different. But the standard deviation was 55, right? And so the standard error was 10 with a sample of 30. The standard error was 10. I'm only one standard error above that. So that's like no big deal. That is not statistically significant. It's not statistically significant. It's totally within the realm of sampling error, of the natural variation. Okay, let me click on this so you can see it. There we go. Let's go ahead and take a screenshot. Oh, I need to get, hold on, let me back up. There we go. Let me get it all. How much do I want? Yeah, I want it all. Okay. There we go. Go. Okay, copy, delete, go back, come here, boom, paste that. Okay, on to the next. Statistics students believe that the mean score on the first statistics test is 65. That's what they believe. And as a statistics instructor thinks the mean score is higher than a 65. That sounds like an original claim to me. And so what does he do? He samples 10 statistics students, and obtains the scores, and there's the scores. He performs a hypothesis test using a 5% significance level. The data are assumed to be from a normal distribution. Okay, that's great, because that's one of the assumptions that we need. Now, does it say that it's a random? He samples. Okay, well, let's assume that he's using a random sample. All right, what kind of a test do you think this is? Which test is this? This is test 3. It's got to be, because there's no mention of a standard of a sigma. Sigma is what? We don't know. Therefore, test 3. All right. Right off the bat, we can see that. Okay, so here's what I'm going to do. Now, watch. I'm going to come up here. And, well, no, where do I want to go? I'm going to come up here. I'm going to copy all of this. And this is what I recommend you do. Hold down Shift, move your arrows, Command C. Let's go below football. Let's go right here. Command V. There it is. Okay, I'm going to call this Stats Scores. All right. Let's go ahead and update a few things now. So, what is the original claim? Is right here. Thinks the mean score is higher. So, the mean score is greater than 65. Now, the opposite of that is that the mean score is less than or equal to 65. Okay, and so what's my null? Well, it's going to be equals 65. What's my alternative? It's the leftovers. There we go. Okay, now is there a significance level given? Yes, there is. 5% it says. So we'll go with that. Okay, now the test statistic. This is different because this is, as we said, this is test 3. So it's not going to be a z equals. It's going to be a t equals. We're still going to need x bar. We're going to need mu. We're going to need n. But we're not going to have sigma. There is no sigma. It's going to be s. S equals. Okay, now, where do I get my x bar and my s? I get that from the data. And there is the data. 65, 65, 70. 67, 66, 63, 63. And then 68, 72, 71. There it is. I'm hoping this is 10. Let's just select. It doesn't tell me how many there are. I think there's 10. Let's go ahead and find our x bar equals mean. Oh, there's no mean. Average. Boom. Enter. 67 is the average. All right, so I'm going to say x bar equals right there, my average. X bar equals that. Okay, and let's, while we're over here, let's do S. S equals ST dev. If I want to take the standard deviation, that's what I'm going to need to do right there. Of those 10, 3.19. Okay, great. So now my standard deviation is there. Okay, now n is not 15, is it? It's supposed to be 10. And then mu is not 16, it's 65. Okay, let me take a hard look at this. 67, 65, let's see, 67 because of my mean there. N is 10, S is, yeah, there it is. Okay, that's it. But notice what happened because I copied and pasted. Let's look at this formula. X bar minus mu, which is the red one, S divided by square root of n. That's it. All right, cool. So my test statistic is 1.97. All right, let's go to p-value now. So this is a t-distribution now. It is totally not normal. It's close, but it's a t-distribution, so it requires degrees of freedom. And so my degrees of freedom is going to be this thing, -1, right? That's your degrees of freedom. I could see that on my handout here. Degrees of freedom is n-1. That goes in the t-distribution. See, I'll show you. Equals t dot inv. Oh, but look at this. T dot, oh no, not inv, t dot dist. T dot dist, and then look at these other options. I've got dot 2t. I've also got dot rt. Now, which one's this one? Look at my alternative. It's greater than. This is a two-tailed test. Sorry, this is a right-tailed test. So I'm going to go t dot dist dot rt. That one. X is going to be that t value degrees of freedom is right there. There's my p-value. There it is. Is the p-value less than alpha? I'm moving on to step 7. Is the p-value less than alpha? Alpha is 0.05. This thing is 0.04. Yes, it is less. I'm going to reject the null. Okay, let's go ahead and adjust this. There is evidence. P equals 3, 4. To suggest, okay, now let's get rid of all of this right here. And again, I'm using suggest because, let me go ahead and write this stuff. Let me write some of this stuff in here. Okay, so this here is the original claim, right? It also indicates a right-tailed test, which we took into account because we used t.dis.rt. Okay, and because this is the original claim, I'm going to be saying support. I'm not going to be saying reject. I'm going to be saying support, and so that's what I do right here. Support or suggests. So there is evidence to suggest that the score was greater than 65 with 95% confidence. Okay, so there it is. See, so if I assume that the score was indeed 65, given my data, that's unlikely. That's only 3.9. Oh, wait a minute, not 3, 4. This should be 40. There we go. 4% chance of that being the case. Now, that's not likely enough for me. Something's most likely up. All right. Let's go ahead and screenshot that and move on. Where's my screenshot? Here it is. Delete. Back to Notability. Scroll down here. Boom. Paste. Okay. June believes that 50%, oh, this has got to be test 1 because it's a proportion. June believes that 50% of first-time brides in the United States are younger than their grooms. She performs a hypothesis test to determine if the percentage is the same or different from 50%. June samples 100 first-time brides, and 53 reply that they are younger than their grooms. For the hypothesis test, she uses a 1% significance level. All right, I think we should be able to knock this one out pretty quick. So this is first-time brides. And it might be a good idea for you to pause the video and go through all the steps and just see what you get. Step 1, the original claim. I forgot. Let's see now. Believes that 50% of first-time brides in the United States are younger. Okay, so the original claim is going to be that the proportion of first-time brides is 50%. See, that's what she didn't say less than, she didn't say greater than, she said is 50%. So what's that going to be in math? Well, that's going to be P equals 0.5. Okay, let's do step 2. Well, the opposite of the original claim. It is not, okay, it is not 0.05 or 0.5. P option equals, gives me not equals, 0.5. Okay, step 3. Null hypothesis equals, let's see, that's going to be this one. Whoops. Right? Because whatever one has equality becomes a null hypothesis. The alternative hypothesis is going to be the leftovers. So that's going to be this one. Command C, paste that. What are some things that this suggests? It's a two-tailed test. Right? Because it's not equal to. Data that suggests that it is greater than, that proportion is greater than, or less than, both contradict the null hypothesis. And so both of those we are going to include in our p-value. Okay, now notice that this one here now was the original claim, meaning we are going to say reject. Well, let's see. Yeah, we are going to use, I should say, we are going to use the word reject, okay, because that's what we do when it's in the null hypothesis, when the original claim is in the null hypothesis. We either accept or reject the null hypothesis. Okay, so step 4 now. Significance level, alpha. If you'll recall, I believe it was 0.01. Now it's time for step 5. Okay, so we already established that this has to be test 1 because it's a proportion. So that's going to be a z-score here. And what do I need? Let's see. I need p hat. I need p. I need q. And I need n. How do I know that I need all those things? Well, it's from this formula right here. Test 1. P, Q. See, they use P0 and Q0, P0, but we just use P for that. All right, so let's go ahead and put this in. P hat was, let's see, was it 53%? Is that what June found? Yep, 53. 53% said that they were younger. P is 0.5, right? That's by assumption of the null hypothesis. Q equals 1 minus P, which again is, of course, is 0.5. And she sampled 100, didn't she? Yep, she sampled 100. Okay, so let's make our standard error. So the standard error is going to equal square root of P times Q divided by 100, close parenthesis. That's my standard error value. What's wrong here? Oh, what did I do? There it is. Great. 0.05. Okay. Equals P hat minus P divided by standard error. You just find the formula. 0.6, not even a standard deviation away. Step 6 now. This is a two-tailed test, and my z-score is on the right side. Go to draw. So what's going on here? Here's the distribution of sample proportions. Right here's the mean, which we're assuming to be 0.5. My mean here is 0.6. And the standard error is 5%. So I reckon I'm 2 standard deviations away. Oh no, 53. Yeah, I'm 0.6 standard deviations away. That is not far at all. So that's going to be like, oh, it's stuck on erase. So that's going to be like right here. Now the tail, two-tailed, you do both sides. That one and that one. All right, so let's go ahead and find this two-tailed probability. So the p-val is going to equal 2 times norm dot dis negative 0.6. Why negative? Well, because this one over here, see, these areas are the same. Come on. 0, 1, 1. Okay, there's my p-value. All right, now, these areas here are the same. It doesn't look like it the way that I drew it, but they are the same. This here is 0.06. Sorry, 0.6. This one here is negative 0.6. Remember, these are z-scores, so the mean is actually, the mean of the z-score is 0. So I put in negative 0.6, and I get the area to the left, and that's this right here, and then I double it to get both areas. All right, so that is my p-value. So now let's do step 7. And let's see, what am I going to do? Step 7 is p-val less than alpha? The answer is no, certainly not. So we are going to fail to reject. So this is not incompatible. This data that I have is perfectly consistent with it being a 50% rate. So that brings me to step 8 now. So there is insufficient evidence. What is my evidence? P equals 0.549, there we go. there's insufficient evidence to reject. Didn't I say we'd use reject? Yes, I did, because the original claim was in the null hypothesis. There's insufficient evidence to reject. We are failing to reject, right? Because the data is not rare enough. There is sufficient evidence to reject the claim that the proportion of first-time brides less than the age, let's see, younger first-time brides that are younger than their grooms is 50% with 95% confidence. Boom, there we go. Enter. All right. Okay, cool. So let's go ahead and screenshot that. Okay, copy and delete. Come back over here. Paste. All right. Now, number 19, number 18, this is a p-test as well. This is going to be test 1, right? Because it's a proportion. It's a proportion. I would like you guys to do this one by yourselves. So take what we did right here, copy and paste it, tweak it, give me a good sensible step 8 that's accurate based on what you find in step 7, and then screenshot it. Okay. Then please fill out the check for understandings and the reflection, and then that's it, guys. Sorry the video is so long. Hope you enjoyed it and learned something, and we'll see you in class.